So can everybody hear me? And more important and equally of equal importance, what would you like to talk about? I can go on talking about general relativity or various other topics. Let me just collapse some of these things, such as these various topics here. Or I can, okay, thanks, burnt cake. I can do a couple of examples, you know, just work out an example, or I could continue and say some more about general relativity or about other topics, probability and statistics, whatever. So what? Okay, so we have one vote for GR. So maybe I should, why don't I start rambling on about general relativity, and then if students think of things they'd like me to talk about instead, why don't you say as much? So the basic point is that we can use all kinds of different systems of coordinates to describe physical points. But when we change our system of coordinates, the points remain the same. They're physical points. Whereas the coordinate systems are conceptual things. And so in particular, differentials transform this way just by virtue of the chain rule. dxi is going to be related to the dxk's in this way, and these are called vectors that transform this way are called contravariant vectors, or if they depend upon space-time, they're called contravariant vector fields. So the photon is for example, described by the electromagnetic field that transforms this way. On the other hand, derivatives transform, again, because of the chain rule, they transform this way. And so partial xk transforms this way, and that defines covariant vectors. Excuse me. So a quantity that transforms like a derivative is a covariant vector. And if it depends on space-time, then it's a covariant vector field. And again, the photon is a covariant vector field. You might say, well, wait a minute, how can we talk about, say the photon is a contravariant vector field and a covariant vector field? Well, the way you go from a covariant vector field to a contravariant vector field is to use the metric tensor, as we'll see momentarily. You can have things transformed doubly covariantly, doubly contravariantly, mixed, and so forth. Einstein introduced this summation convention. This was at a time when doing this on a typewriter was, I guess, impossible. It had to be written in ink, I suppose. These days, of course, we can do that. \sum gives us a sum sign, but in LaTeX. But it's still true that by getting rid of this sum sign, we really save a lot of time, and the equations become easier to understand. We have symmetric and anti-symmetric tensors, and notice that the tensor is symmetric or anti-symmetric only when both indices are up or both indices are down. I think I'm going to skip some of this. The idea of one of Einstein's many insights was that a theory written in terms of tensors, or equivalently in terms of forms, has equations that are true in all coordinate systems if they're true in any coordinate system. And only such generally covariant theories have a chance of being right, because we can't be sure that our particular coordinate system is the right one, the one that nature chose. There are various notations for derivatives. I became enamored of this notation, comma theta for derivative with respect to theta. I think that was actually a mistake. I think this is a better notation. Semicolons are used to define covariant vectors, different derivatives. A point, a physical point in space or space-time with coordinates x is a scalar in the sense that it's the same point in any in any system of coordinates, and what changes is well, the point moves if you change the coordinates that label it, staying in the same system of coordinates, of course. And the way it moves defines a vector in the space that P lives in. And let's think of a sphere for the moment. If we have, I can get the Apple Pencil so suppose we have a sphere here, then we might have coordinates of a particular point, might be, this is the North Pole, and there's an angle here, theta, and then if this is the x-axis here, this angle here is phi, where this line would drop down vertically on the x, y plane. Well, actually, it's y equals 0, so theta is pi over 2 in this case. In any event, if we, for example, increased phi, the point would move like that. So in other words, dp in this case would be the vector phi hat times, times r sine theta d phi, r sine theta being this distance here. Anyway, what I'm trying to say here is that the vector phi, dp, is a vector in 3 dimensions, whereas the surface of the sphere is a surface in 2 dimensions. So what you have with these vectors that I called EI, why does it keep doing that? One of you may know the answer to one of my questions like, why does this keep reverting to an eraser? If you know, please tell me. Anyway, so I said EI of x is the ith derivative of P of x. And if these are points on the surface of a sphere, then the vectors EI are vectors in 3-dimensional space. On the other hand, the coordinates x are 2 coordinates only, theta and phi, And so we have two vectors. We have E theta, which is d theta of P of x, and we have E phi, which is d phi of P of x. These two vectors are complete on the surface. Well, I don't spell very well. Are complete on the surface. Whoops. God. But they are three vectors. They're vectors in 3D, if we think of the sphere as embedded in 3 dimensions, which we normally do. So these EI are called basis vectors. Now the metric tensor, it turns out, is then the inner product of two basis vectors. And you might ask, well, what is the inner product in this particular case? Well, it depends on what G is. If G is describing, let us say, one of the standard cosmologies for our universe, then these vectors are, if we take totally flat space-time, then these vectors are four vectors basically. But if we take them to be, if we take the cosmology to be one in which space is curved, space-time is curved so that or actually space is curved in these cosmologies, and it's either closed or open. So in other words, in the closed space, our three-dimensional space are three-dimensional points on the surface of a four-dimensional sphere. On the other hand, then if we imagine that our universe is open and curved, then our points of three space are points in a four-dimensional space-time. So what we have here is, now in both cases, all three cases for these three standard cosmologies, the three or four dimensional space that embeds physical space is either Euclidean or Minkowskian. That is to say, the vectors are perpendicular to each other. And the metric then here is, let us see where I have a formula for that. It's called a semi-Euclidean space. So so in other words, some of the vectors are, you use a minus sign here in some cases and plus sign for the ordinary space components. The inverse of the metric tensor would be G, say, Li, and that would be such that GLI, GIK, well, we sum over I, and we're going to get, if it's an inverse, then this is delta LK, which of course is just 1 on the diagonal. Just to make a long story short, I mentioned that we might have the photon we might consider as a contravariant field. Well, what is it as a contravariant field? Well, it's GIK times AK. So that you use the inverse of the metric tensor to convert a covariant vector field to a contravariant vector field. And similarly, you can say that AK of X is GKL AL of X. So a contravariant field gets converted to a covariant vector field by means of the metric tensor with lower indices. And the same thing can be said for these basis vectors. EI, in other words, is GIK EK. So our basis vectors can be raised or lowered. One important thing here is, suppose we have a contravariant vector field and we dot it into the basis vectors. Well, then what we've got is something called V of X that doesn't change when we change our coordinates, because we've got one upper index and one lower index. Now that may not be immediately apparent, so maybe I should say what this thing is. So V prime of, let me just see if I can write this a little bit more neatly. V prime of X prime then would be what? Well, what's our recipe? It would be VI prime at X prime, E prime I of X prime. And we know what our rules are for contravariant and covariant vectors, namely that this one is partial X prime I, partial XJ, this is X upper J. X upper J, Vj of X, and this one would be partial partial X prime I, partial X, let us say K, E K of X. And now you see the chain rule summing over I gives us delta Kj, Vj of X, Ek of X, which is just Vj of X, Ej of X, which is what we called V of X. So this V of X, so V is a scalar. And that means then that partial V, partial XL, and I'm basically following this equation here, is, well, kind of. It's, let us say, to fill, I'll change I to J here. Partial V, J to I should say. So that's what we have. And now we can say that this is a covariant vector. So this is a covariant vector. And we say that this is that the right-hand side is a covariant derivative. So we'll call this dl of vi. and we see that it's equal to partial VI partial XL EI of X plus partial EI of X partial XL VI of X. And now what we can do is we can take the inner product of that with, say, EK. And so we take EK dotted into DL VI. What that gives us here is partial VK partial XL, because EK dot EI is delta KI. And right, okay. And then we have over here EK dotted into partial EI of X partial XL VI of X. And this thing here is a special thing called it's called an affine connection. It's called a Christoffel connection. It's called a Christoffel symbol. It's written typically as gamma K IL, and that's EK dotted into partial EI partial XL. So the way I'm thinking of this, this dot product is the dot product in the higher dimensional Euclidean or pseudo-Euclidean space. In any event, the bottom line is, maybe I'll switch to blue. The bottom line is the covariant derivative of a contravariant vector is the nth derivative of the kth component of the contravariant vector plus gamma K IL times VI. And this is something that occurs in gauge theory, non-abelian gauge theory and abelian gauge theory. And so, for example, the nth derivative of a fermion field, let's just call this a charged field rather than get involved in gamma matrices. So this would be dl of psi plus al psi, where al is either a matrix of gauge fields or just a single gauge field times I times an electric charge, something like that. So this is the photon as an example. Okay. I think we can skip some of this. If you take the covariant, let me, in as much as, let's see. Okay, double tapping the pencil makes it possible to switch to eraser modes. All right, so I have to be careful about double tapping. Thank you, Anon. Let me just say what the, this is even worse. So let me go over here. The covariant derivative then of a covariant vector, well, this will be clearly, it'll be the ordinary derivative, but then it turns out to be minus gamma K IL VK. The derivation of this is in the book. I think we can skip a lot of this. Now, the when I mentioned previously that one takes, what is the dot product of EI with, say, EK? Well, this is a pseudo-Euclidean space, or even a Euclidean space. And so it's some eta alpha beta, EK beta. We were summing over alpha beta, and this eta is, maybe it'll be a minus on a couple of these, and then it'll be +1 on the others, however many there happen to be in this higher dimensional space. So remember, you think of a surface of the sphere, two-dimensional space, but embedded in 3 dimensions. Our 4-dimensional spacetime is embedded in some higher Euclidean or pseudo-Euclidean space. Pseudo-Euclidean just means that the metric, the inner product of vectors has some minus signs. And so we have here that GIK is equal to EI dot EK, which is, again, E alpha I, eta alpha beta, EK beta. Now, with all this complexity, you might wonder, well, this is really getting awfully complicated. Sometimes it is, but look at what happens if, suppose we have a matrix that is anti-symmetric. Then what happens? Well, you can show that dk of AIL plus dl of AKI plus di. All right, I already screwed up. These are covariant derivatives, so let me make these covariant derivatives. Di of ALK is simply the sum of the ordinary derivatives. That's an I. That's an L. So sometimes things are simpler. This is something that Luigi Bianchi discovered. And in particular, the Maxwell field strength tensor, FIK, is an example. FIK is minus FKI. And the homogeneous Maxwell equations, there are 2 of them, they are just examples of the Bianchi identity. And they're tensor equations. Okay, so let's go on to what gamma is. And it turns out that, I'm not going to go through this here, but gamma KIL is, we come down here, it's a half GKJ summed over J, of course, GJI. Oh, I'm using this common notation. So all right, let me revert to the more standard notation, which is probably a better notation. GNI plus DIGNL minus DN GIL. And so this basically tells you that the thing that you need for covariant derivatives, and in fact everything else in general relativity, apart from how fermions interact, can be related to G, the metric tensor. And the way you find the metric tensor is you just use the fact that the invariant is GIK dxi dxk summed over I and k. And so by doing just 4D geometry in our four-dimensional space, you can figure out what GIK is. Now that's easier said than done. If you happen to be an ant living on a sphere, you can work it out if you're a very smart ant. But of course, we're in four-dimensional space, time, and we still don't know if the universe is open, closed, or flat. All experiments so far are consistent with flat. And in fact, there are the more modern cosmologies with supported by the cosmic microwave background observations indicate that the universe not only is expanding, but that the expansion is accelerating, and that means that it's getting flatter, that space is getting flatter and flatter and flatter. And also experiments indicate that if you look on large scales, the universe seems to be homogeneous and isotropic. And if you put together those two ideas, homogeneity and isotropy, and say, well, let's just say that space is maximally symmetric. Well, it turns out there are only three spaces that are maximally symmetric. You combine them with time, and then you have a scale factor A of t. Now, I don't know why that happened. We have then a scale factor A of t that says how space is expanding. And then we say space is maximally symmetric. And that gives us our three Robinson-Walker, Friedman, Robertson, Walker, Lemaitre cosmologies. All four people should be quoted when we talk about them. Lemaitre wrote in French and was Belgian, and he was a priest actually, and apparently he was rather caustic also. Anyway, so he hasn't gotten a lot of credit, but he deserves as much credit as Robinson Walker, most people think. In any event, I'm sorry I got off on a tangent and then stopped. If we just look at this, we see that doing geometry, you can figure out what GIK is. Knowing GIK, you can figure out what gamma is. So then you can compute all the things of classical Einstein general relativity. And that was one of Gauss's observations 150, 200 years ago when he was writing. What he showed was that all you need to do was to make measurements in the surface. So on the surface of the sphere, in our four-dimensional space, you don't need to know how the surface is embedded or how our space-time is embedded in a larger pseudo-Euclidean space. And that is indicated by these equations, namely that geometry gives you GIK, and then GIK gives you the gamma matrices. That is to say, so geometry gives you this, and then with this you can get all the covariant derivatives. And so you can do everything by understanding the space or space-time you live in. You don't need to think about embedding it. Nonetheless, I think it's a lot simpler as human beings to imagine that these things are curved spaces in a larger flat space. Unfortunately, if we take the cosmology in which space-time is open, or space is open, then we have two time coordinates, and that's kind of confusing. It's very amusing though. All right, let's see. I think maybe I'm going to skip parallel transport, go to curvature. Well, this is what's called the curvature tensor. And it's kind of like the commutator of two covariant derivatives, which is one way of getting the Maxwell field strength tensor. That is to say, Fik is di plus ai commutated dk plus ak. And so what is this? This is di ak minus dk ai plus ai ak minus ak ai. If these are matrices, and as in a Yang-Mills theory, then this is a matrix structure. If we're just talking about electrodynamics, then these two terms, at least classically, would cancel. In fact, they even cancel quantum theoretically, quantum mechanically. Okay, I hope. Let's look at, let me just, a message to students. I'm perfectly willing to jump back to doing some examples, because in fact, what I did do as preparation for this class was not review general relativity, but instead I prepared two or three examples, or 3 or 4 examples, I don't remember exactly, that I would work out in class. By the way, I'm a little worried. I don't see a border on this. Can you guys still see? Am I still sharing?
Yep, we can see just fine.
Okay, so there's been a request for some of these, some examples. All right, why don't I stop, because now stop the GR and encourage you guys to read the book on GR if you want to, and I'll skip back to some of these examples that that I prepared. So let me try to find them here. So I think we talked about this already. I think we talked about this example also already. And I think we even did this one already in class. Tell me if I'm wrong. Say so. So let me work out for you the something about the spherical Bessel function that I just sort of waved my hands on when we were going through it in class. Remember the spherical Bessel functions. I almost call them the spiritual Bessel functions. Anyway, they're the nice Bessel functions. And when you first look at the definition, you'd say, well, this is a very complicated series. And now we've just made it worse. But in fact, somehow we've made it better. And let's look at it at small x. So if we look at the definition, the series 1010 for the cylindrical Bessel function for a general real argument, nu, it's 1 over gamma nu plus 1, x over 2 to the nth power, and that's the lowest order term. The other terms are higher powers in x. And so JL then, which is equal to this, is then given by this expression. Well, what is nu plus 1? Well, nu is L plus a half. So this is L plus a half plus 1. That's L plus 3 halves. Nu is L plus a half. We've got a square root. And now you see why the square root in the definition actually helps. It doesn't make things worse. It cancels the funny square root here. And so we just get x to the L over gamma. And back in chapter 5, I gave you formulas for the gamma function of half integer, that is n plus a half integer, integer plus a half integer, and they're of this form. And so now we have to figure out what L plus 3/2 is. And if you just straightforwardly, wow. All right, we can keep this, I guess. You then plug in n equals L plus a half, and you get this expression. After some cancellations, you get that. And then finally, that's the same thing as this. And then you notice that these L factorials and 2's help you reduce that to a 2L plus 1 double factorial. And so that's the original approximation 1073. And if I go back to chapter 10, I can show you 1073, and this would be spherical Bessel functions. Boy, there's a lot to go through here. Oh, sorry, I have to go to, well, now I'm even confused myself where these things. So there's the original definition. And the approximation for small rho or small x here was rho to the L over 2L plus 1 double factorial, and that's the same as this. I think we can also just derive the large rho approximation. And the large rho approximation is when you see if all the rho derivatives hit the sign, they just turn sine into cosine, and these are things that are of the same order of magnitude, namely varying between -1 and +1 all the time. And so we just let all the derivatives act on sine rho, and so we just can compute this. Now, if you stay with sine and cosine, then the nth derivative of sine rho is kind of hard to do because sine goes into cosine, cosine goes into minus sine, and it's hard to keep track of. On the other hand, if you use our very nice exponential representation of the sine, then it's just the nth derivative of this. And L derivatives with respect to rho just pull down I to the L, which with the minus sign gives us minus I to the L. And then over here, we're pulling down minus I to the L. And so the -1 to the L's cancel, and we just get minus I to the L. And minus I is minus I pi over 2 to the L. And then this one is the I pi over 2 to the L. And just rewriting that in a straightforward way, making 2 latex errors. My goodness, all right, I've got to fix that. This is of the examples section. Okay, well, that's better. Let's see if I can probably do it on the fly. So let me do it on the fly. Right, I think it's just, there's a parenthesis there. And another parenthesis there. Let's see if that works. There we are, okay. So that gives us sine rho minus L pi over 2. And that in fact was the approximation. JL of rho equals that. You might say, well, what about all the rows? Well, we've got L rows here, L rows there, so there's one left over. So we have to divide this thing just by row. And so that gives us our formula for, let me make this bigger so people can see better. So that gives us sine of rho minus L pi over 2 divided by rho. And these are the these are the ways that the spherical Bessel function behaves. Let's see if I've got a figure for that somewhere here. Somewhere here. There we are. All right, so these are the spherical Bessel functions. You see J1 and J2, they go as rho or rho squared, and then they go as sines there. So there's the rho to the L, and then down here we just have a sine wave. And of course, the sine wave doesn't, you have to go to rho equals 5 or so before you get more or less a sine wave. All right, so that was this example for Bessel functions. So that's what I prepared for Bessel functions, but I also did something for the previous chapter here. If I'm not, no, that we're not there yet. So let's go back. Right, I thought I would do this one for you. The electrostatic potential inside a hollow sphere. This is kind of related to one of the, it's similar to one of the homework problems. And what we're saying is that we have a hollow sphere of radius r, and the potential on the sphere is this. So we know what the potential is on the sphere, and otherwise we imagine that there's a sphere in vacuum. So I probably should have said in vacuum. So inside the sphere, and we're only examining the sphere, the region inside the sphere. We're not talking about values of R bigger than capital R. So inside the hollow sphere, the potential obeys Laplace's equation. That's because we're assuming that it's in vacuum. So I should have said in vacuum explicitly. And so since it satisfies Laplace's equation, we can use the expansion 9.86, which is a polynomial, Legendre polynomials, and then r to the L and r to the minus L minus 1. What we're taking advantage here, is that we actually have spherical symmetry. And so spherical symmetry gets us a lot. In particular, there's no phi dependence. So we have azimuthal symmetry, but we have more than azimuthal, we have spherical symmetry. And potential's finite at the origin. We're assuming that the potential then is finite at the origin. We don't have any charges at the origin. So all the BLs have to vanish. We just have this then. And we satisfy the boundary condition V0 cosine squared of theta. And we have this sum AL R to the L PL of cosine theta is V0 cosine squared. Well, looking at the explicit formulas for the Legendre polynomials with x equal to cosine theta, we can, what are we doing? We're looking for x squared. So we can see that x squared is 2p2 of x plus p0 of x, all that divided by 3. And so the boundary condition is the sum of AL, RL, PL of x is V0 over 3, 2p2 of x plus p0 of x. And then we have an orthogonality relation for the Legendre polynomials. And that orthogonality relation gives us that some AL, R to the L, PL, PN is just going to give it, we're going to have, the integral is going to give us a delta NL times 2 over 2n plus 1. So that's 2an r to the n over 2n plus 1, whatever n is here. And in this particular case, what we've got is since we have this combination of n, we get 2 over 5 delta n2 plus 2 delta n0. And that tells us that the coefficients are n equals 2 and n equals 0. And that gives us this as a final expression. And so that's the final answer there. I think I did another example here. Let me lower the magnification. Well, not that much. Let's be reasonable and go to something like that. And I thought I did some more. Did I? Well, no, I guess maybe I didn't. Maybe I was going to do something and didn't get around to actually doing it. All right, let me do something simpler. So let's look at, well, actually, you know what? I think what I'm going to do, instead of doing that, is I'm going to do another example well, let's do two things. Let's do one that I sort of prepared to do. So let's see if I can get this once a face ID. All right, let me switch to say blue now. And let's just consider a differential equation problem. So we have y prime plus xy equals c e to the minus x squared over 2. So I'll try to work.
You bring the whiteboard up.
Oh, yeah, thanks. And I suppose I can, well, I thought I could make that bigger, but I don't know how to make it bigger. So, all right, let's just go with it the way it is. So we're going to use the method of section, there's a general method for solving first order differential equations. And so what we're going to do is we're going to set R of x equal to x, that's this thing here. And then we're going to set S of x equal to c e to the minus x squared over 2. And let me maybe show you what I'm quoting here. So if we go back to differential equations, let's see, where was it? Was it here? Yeah, linear, yeah, here we are, linear first order ordinary ODE. So this is what we're talking about. And using this then, what we can, in fact, we can make this a bit bigger if people would like to. So this is a general method of solving this. And so we just go about it. And what we do is we then say that we compute alpha of x, which is here. And so alpha of x is equal to e to the integral r of x dx. And that's e to the x squared over 2. And so then our general solution is y of x is equal to y of 0, e to the minus x squared over 2, plus e to the minus x squared over 2 times the integral c dx. And so y of x is equal to y of 0 plus cx e to the minus x squared over 2. So you notice that the way I've worked things out, y of 0 is then equal to y of 0 plus 0 e to the minus 0 squared over 2. So this is just y of 0. So we've got the boundary conditions correctly satisfied. Let me now jump to something that I could do one more example. Would you like to see another example like, oh God, another example like, oh, I didn't do it there. All right, hold on. Would you like to see another example? Let's just like, oh, it wasn't Bessel functions. What was it? Yeah, here. Would you like to see another example like this?
Totally.
All right, let's jump to that. So let me, all right, now I want to be a little bit careful here because I want to do what I need to do is I need to find, let's see. So the homework problems were 12, 13, 14, and of chapter 9. And let me just look at this. I don't want to do one of the homework problems. Bad enough that I assigned the same homework problem twice. All right, I can do 9.18 then, and that is find the electrostatic potential outside a hollow sphere if the potential on the sphere is same potential. So it's essentially the same problem. And so let me let me do that. So once again, what we have is that we can say that the expansion is of this form because we have spherical symmetry. But now what we're talking about is a hollow sphere with presumably some charge on it, so that there's possibly some charge on it, but that the potential at infinity presumably falls off and goes to zero. And so we can drop all the AL terms and just keep the BL terms. So we're assuming that which is perfectly reasonable, that the potential goes to zero at infinity. And so what we have then is V of R and theta is then a sum BL over R to the L plus 1 PL of cosine theta. And once again, I've forgotten to, oh, let's see, we don't want that. Let me just quickly switch to something that's a little more reasonable. We want to do, I don't know if it's quite spherical harmonics, but it's, at least it's in this general vicinity. Right, there, I guess is a good enough place. So what we now do is we want to satisfy the boundary condition. So that's V of capital R and theta, which is going to be this sum BL over R. Well, now it's capital R to the L plus 1. PL of cosine theta should equal V0 cosine squared of theta. And so what we do is we want that this, what we are able to see is that x squared, once again, we use the same relation, 2p2 of x, that's a 2, plus p0 of x divided by 3, that's just x squared. And so we say, well, sum of BL R to the L plus 1 PL of x is then V0 over 3 times 2p2 of x plus p0 of x. And now we use the orthogonality relation, the one that I used before. Right. This orthogonality relation, we just use it for this particular case here. And what we do is we find that the integral of the sum BL over R to the L plus 1 PL of x integrated Pn of x dx.
Can't see the whiteboard.
This is going to be then an integral of the same sum BL.
Could you bring the whiteboard to the front, please?
Oh, damn it, yes. Thank you. And this orthogonality integral then is, wow. I don't know, these touch screens have some problems. So we have a delta NL here. So this is 2 over 2n plus 1 delta NL. This is a sum over L. And at this point, I need to get rid of the integral sign. So finishing this sum, what we have is 2 over 2n plus 1 times bn over r to the n plus 1. And we want that to equal v0 over 3 times 2 times 2/5 delta n 2 plus 2 delta n 0. And when we unravel all that, we get that bn is equal to 2n plus 1 v0 r to the n plus 1 over 3 times 2 over 5 delta n2 plus delta n0. That's an n. So with that, what does that mean? That means that B0 is V0R over 3, and A2 I have written here. I guess that must be B2. B2 is 2V0 R cubed over 3. And so the potential V of R and theta is V0 over 3 times R over R. Let me just erase some of this junk here. R over R plus R cubed over little r cubed, 3 cosine squared theta minus 1. So that's the final answer for this particular problem. Of course, you know, this is just the way I did the problem. There's always the possibility that I made a mistake, and I'm particularly grateful to students who correct my mistakes. It's much better to get an error corrected sooner rather than later, or not at all. So anytime you think I'm doing something wrong, please speak up or send me an email. Of course, sometimes you won't be right, but if you're right and you point out a mistake, I'll be very grateful. Okay, let's see. We've got 6 minutes left according to the clock. What would you like me to try to do in 6 minutes? I think I obviously have to turn notifications off to some extent, but shall I just go on and do a little more relativity? But, you know, if this, all right, do you have any other examples? Well, let's see. What area would you like to see an example done on? Would you like to see one of the earlier chapter examples? Chapter 10, because you want help doing the homework problems. I think we've kind of done let's see. All right, let's see if I can squeeze something in here. But I don't want to do a homework problem. Notice that the ones for Sunday are, I assigned one from chapter 9 and then 4 more from chapter 10. Well, I could start this one. I don't know if we have enough time to finish this one. So let me see if I can find. So this is. All right. Well, let me see if I can squeeze this in. So first, so this is the problem that I'm going to try to do, show this, and now that I've exposed the, let's see, I feel like switching to a different color. Let's try green. Okay. Let me just make absolutely sure that 27 is not one of the homework problems. No, all right. Okay, so basically the first thing to notice is that K dot R, what is that? Well, it's KR cosine theta, where K is this vector, R is that vector, theta is the angle between them. And K here is the length of the 3 vector K, R is the length of the 3 vector R. And in ordinary quantum mechanics, the inner product of the bra for the position R and the ket for the momentum state K, this is e to the I K dot R over 2 pi to the 3/2. And now we have an addition theorem, an expansion, 103, so 102, 103, and well, there's the expansion right there. And so what we have is that this e to the I KR cosine theta, this is e to the I KR cosine theta because of this relation, and over again 2 pi to the 3/2, and then we can expand, if we jump back to this equation, e to the I KR cosine theta is then this sum here. So this is 1 over 2 pi 3/2 times this sum over L from 0 to infinity, 2L plus 1 PL of cosine theta, I to the L, JL of KR. And so we have that expression. And then we can, using this expansion, we can say, well, that's 1 over 2 pi to the 3/2. And then this is a sum, L equals 0 to infinity, sum M equals minus L to L, 4 pi I to the L, JL of KR, YLM of theta and phi times Y star LM of theta prime and phi prime, where the theta phi correspond to R and theta prime, phi prime correspond to K. All right, so we're just about out of time there. I'll put all these, the example file, the new note file on the class web page, and I'll put this lecture on YouTube, and I guess that'll be that. My plan is to hold class tomorrow, Wednesday, also Thursday. And then instead of a final exam, I'll just give a lecture that will occupy the time period that the registrar in his wisdom has assigned to this course for its final exam. You can thank the pandemic for the absence of any exams, well, sit-down exams. Anyway, stay healthy. This is a terrible illness. So you want to stay out of crowded indoor settings. That's the worst, is crowded indoor settings. I heard on PBS and NPR tonight, some guy was very careful on flights, and then he found himself changing planes at an airport. And so he wound up being on a crowded airport's train that took him from one part of the airport to the other. And there were so many people that he caught COVID-19. I'm not sure why it is that a mask didn't protect him, but maybe he didn't have a mask. I don't know. All right. Well, goodbye, everybody. Stay safe and have a nice evening. So I'm going to stop